Okay, so first up, I just want to show everyone. Okay, just as a reminder, if you go to course content and under miscellaneous, you actually see the Declaration of Honesty in Academic Work. Please do fill it in before the end of this weekend. Okay? I've set a so-called deadline for this. It is treated as an assignment, but I hope that you can just fill it in by this weekend, just so that we have everything in order. If we don't, then, or if you don't, I may have to assume that you're intending to cheat. It's, I think, something that people generally don't intend to. Okay, so don't forget. And also, of course, if you go to course content, problem set 1 is available. Deadline is this coming Sunday at the end of the day. And after today's lecture, the next problem set will be made available. So just a few questions to kind of get you into the just get you into the mood to do these calculations, and then we'll move on to more difficult ones. Okay, so that's in terms of the administration. Is there any questions or comments about this? About the administration? Let me quickly check if there's anything on the discussion board. Any questions about the administrative aspects? Okay. If not, then I suggest we get started. So let's share the screen on this here. Here. Okay, that looks good. Okay, so let's start with with the usual, with the recap. In particular, I hope everyone recalls what we did last time. So let's take a quick look at the recap. And so last time we really focused on integration, integration of fields. So these are, for example, integration of a scalar field and the integration of vector fields. Generally, there are three types, right? So if we think about it in terms of integration of fields, consider we consider, for example, path integrals. So, for example, we consider this one, where phi is some scalar field, or we have path integrals in terms of a vector field, in this case, a dot product with a line element, or even, if you will, a cross dr. And in this case, this dr here is just any old path that you can think of, or if you want to decompose it, you can think about it in terms of, let's say, ex dx plus ey dy plus ez z. Okay. So indeed, we can consider this integration over scalar field, vector fields, and with vector fields, there's a dot and a cross products that we can. Okay. So similarly, we have surface integrals. So we can consider surface integrals. And these also come in different shapes and different forms. So I'll try to, try my best to make sure that I write things like double integrals. In this case, a double integral of a scalar field, or we have a double integral of a vector field, in this case, the dot product, or again, we have cross ds here. In this case, the surface element here is basically, again, what we've discussed before. If we have, some particular surface here, this is a surface element, then, the direction, right? ds is here written with as a vector. Then the direction is the vector pointing normal to the surface, and then of course the actual surface element itself, the size. And so, for example, here this is dx, and this is dy, and then this would be z. So in this case, this is ez dx dy. Okay. And then finally, if we also consider volume integrals, in which case we are looking at triple integral of my scalar field dv or some vector field. In this case, note that dv, the volume element, is a scalar, and so we only have two flavors. And in Cartesian coordinates, this dv is just typically given by dx, dy, dz. So that's pretty much where we started off with. And the reason why we looked at these integrals is because we wanted to ultimately construct the an understanding of these differential operators that we started with looking at fields. We wanted to put them in an integral form. For example, the gradient can be written as an integral as well. So this is something that we've looked at last time as well. And so, we can write differential operators as integrals. Please give them an integral formulation. And so one example is the gradient, which we can write as the limit of some volume v goes to 0, 1 over v, and then the integral pi over some surface. Yes. So ds in this case is the bounding surface of volume v. Okay. And then we can actually do the same thing for the other ones. So, for example, the divergence of A can be written as the limit of v goes to 0 of 1 over v surface of A dotted with ds. And finally, also cross product as the limit of v goes to 0, 1 over v surface integral of A. We'll do the correct sign. It should be dsa here. And so, for example, by looking at these, by looking at especially the divergence and the curl, hopefully you realize that indeed these two are two ways of representing the field. Right? One is the component perpendicular, to this ds, this volume that we are constructing, and the other one is normal, is along parallel to the surface. One is the divergence, and so one is the curve. Okay, so having done all of this, having constructed this picture, we can actually move on, or we moved on to prove two important theorems that actually come across quite often. And so the first one is Gauss's theorem. Sometimes it's also referred to as the divergence theorem, which simply states that when I have the integral of a divergence throughout a particular volume, then I can actually equate that to surface integral like this. Okay, and so we've actually used this to turn the divergence of the electric field and the divergence of the magnetic field into their integral formulations. And the other thing that we did was we looked at so-called Stokes theorem, which is the more or less the equivalent then for the curl. Look at Stokes theorem, then the integral of the curl of A over some surface ds given by, let me do this properly, this is then the integral over some loop A dot dl. And so for both cases, for the top case, ds is simply the surface bounding V, and the C here, this S, the C here is the bounding kind of line to a particular surface that we're integrating. So naturally, these using Gauss's theorem and Stokes' theorem, we are actually we're able to re-express the Maxwell's equations in a particular form. So let's continue this. So now we have that Maxwell's equations integral form. Then given by the following. So if we have that the properly, so the integral of E S is proportional or is equal to Q epsilon naught, where Q here is the total charge enclosed in X. And similarly, we can look at the curl of E, which simply states that the integral of E dotted dl equals to 0. We're actually going to pay special attention to this equation over here later on this lecture. Okay, so now in terms of the magnetic fields, we arrive using the divergence theorem or Gauss's theorem, E dot ds equals to 0, because the divergence equals to 0, and the loop integral of B dl equals I, where I is in this case the current. Okay, let me out. In this case, I is just the total current passing through surface bounded by see here, S and S. Okay, so these are Maxwell's equations in integral form. And the other thing that we managed to do by considering things in integral form is to obtain an expression for charge conservation. We arrive at a particularly simple expression for the charge conservation where it's the partial rho partial t, right? Is the rate of change of the charge density plus the divergence of J equals to 0. J is the current density. And so this here is an expression for the charge conservation. Okay, so that's pretty much a recap of what we did last time around. And I think this would be a good initial moment to take a quick break to see if there are any questions. But I suggest that we reconvene at 2:56. Come back and then we'll get started on looking in this case at the potentials because we have established Maxwell's equations, but we will see that we can actually have a slightly alternative formulation where instead of using the electric and magnetic fields, we can actually use so-called potentials, which are a scalar field and a vector field. We'll take a look at that after the break. I'll see everyone at 2:56, 4 minutes from now, and yeah, see you guys in a moment. Okay, welcome back, everybody. Let's continue today's lesson. And as I mentioned right before the break, we're going to actually take a look at, instead of considering the electric field and the magnetic field, we're going to actually try to express them in something else. And in order to do that, we have to go back all the way to, I think it was 2 or 3 lessons ago, where I introduced the so-called Helmholtz theorem. Because it's quite an important theorem, I'm just going to state it again, and it's going to be the basis of the work that we're going to do today. So Helmholtz theorem basically states the following: that we can write, any vector field F. We can write it as the following: F equals to gradient of phi and the curl of A. And in this case, there are 3 conditions. Phi is a scalar function. A is a vector function. Okay? And the third caveat, that the divergence of A is specified. Okay? And I hope that everyone can still remember why, in this case, the particular case that the divergence of A has to be specified. Okay? And for those who just as a recollection, as we went through, right? If we take the curl and the divergence of F, then we realize that they both reduce to a Poisson equation, which is uniquely solvable, provided that the divergence of A is. This is basically the start of our exploration today. And so the question, or the thing that we're going to explore, is whether can we write electric field and magnetic field in terms of phi and A, which in this case we will simply refer to as potentials. And the reason why they're called potentials will be clear in a moment. It's something that you probably have seen in 2041 as well. But for our sake, it's something that basically generates or specifies a particular vector field. Okay, so that's Helmholtz theorem, and let's see if we can rewrite things with this in mind. The first thing I want to do is look at the electric field. Let's take a look at the electric field. Now, let's recall that the electric field is irrotational. What does this mean? This means that the curl of E equals to 0. Okay, so that's the first point. The second point is that indeed that the curl of a gradient is always 0. And so if I take the curl of a particular gradient, then I always get 0. So if I compare the first equation with the second equation, I ought to arrive at a conclusion that electric field can be written as a gradient. In this case, the proposal is to write E as a negative gradient of phi. So in this case, phi, the scalar potential, is the scalar potential. And the negative sign is actually there for convenience or convention. But if I take a look at, for example, the last slide here, here is also even Helmholtz theorem is convention where we have a negative sign. Okay, so already we can see the following. We can see that if I now replace this f in this equation, I can see that E is specified by some phi. In this case, A is not necessary. So the electric field can be specified by simply a scalar function alone. That opens the door for a lot of, a lot of calculations, right? We can make calculations much easier by considering only a scalar function for scalar field rather than a vector field. Right? Vector field has three components, has direction and everything, whereas a scalar field is simply a number at a position in space. Okay, now let's take a look at properties of fields that are that satisfy this. Okay, and that's the first thing we'll do. So I want to introduce the concept of a conservative field. Conservative fields. Okay. What does it mean for a field to be conservative? So if a field is conservative, if a field F conservative, then if I go around a loop, if I take F around a loop, then I must arrive, conservative fields, I must arrive at 0. Okay. Now, we've seen this before. For example, if F is a force field, right? So imagine F to be the force to be the gravitational force, for example, then the work done, which in this case is indeed F dotted with dl, right? It's integrating F over a particular path. Then the work done equals to 0. Okay, so that is what we call a conservative field. But if a field is conservative, right? So if I go around the loop and if I integrate around the loop, then I arrive at the same value for F, so that the differential is 0. So we can re-express this as a condition on F as well, on F directly. So if I take a look at here in this case, the recap where we have Stokes' theorem, we can indeed see that we can take the integral of some vector field A, we can turn this into a surface integral. So rewriting this f dot dl equals 0, I can also state that I get the curl of f. A bit more clear. That the integral of f dl equals to of the curl of f dotted with ds equals to 0. but the surface S, the line C, but this result should hold irrespective of exactly which C I take, right? This result should not hold if I take this loop or if I take a bigger loop. And so this whole result should be independent of S, and therefore I have that the curl of F equals to 0. Okay, so indeed, if the curl of a particular field is 0, then I'm dealing with a so-called conservative field. Any questions? Okay. If not, then let's move on. And we can actually further consider the work done by, let's say, electrostatic fields. So in order to give an interpretation, work electrostatic field, in order to give an interpretation of this potential, you can actually consider the work done by of bringing or moving a charge around. Work done moving charge Q is simply given by F, the force, multiplied with dl, which we've seen in one of the first lectures, that is simply Q E multiplied with dl. So let's make this a small piece of work. Now, we just arrived at the result that the E field can be written as the negative gradient. Okay? And so I can further write this as minus Q gradient of some phi and dotted with dl. This here, I recall the explicit expression of the gradient again. This is Q. So again, just as a recollection, this is partial x dx in the x direction plus partial phi partial y in the y direction plus partial phi partial z in the z direction, and dl is simply given by dx ex plus y ey plus dz ez. And if I take the dot product between these two things, I take, the dot product is of two vector fields is simply the x components multiplied, the y components multiplied, and the z components multiplied. And so I simply get something that's q partial x dx plus phi partial y dy plus partial phi partial z dz. So finally here, this is simply the expression for q, and this is just a small change of phi. Actually, did my screen just die? Can people still hear me?
Yeah.
Okay, but I think my video has died.
Frozen.
Okay, I'm back. Okay, good. So we can see that a small piece of work, okay, so dW, a small piece of work is in this case directly related to this phi, to this potential. And so this actually allows us to give this potential a particular interpretation. Okay? So in this case, what we have is that this is simply the work, or the, this is the work done. In this case is equal to the decrease potential energy. And so indeed this this phi is related to the potential energy. Potential energy, and actually it's per unit charge. Okay, so that immediately gives us an interpretation of the physics behind this this phi. Now we can even go a step further, and we can even consider this, so we can consider this work also as a this work done is work done goes into the change of kinetic energy. And so also what I can do is Q E dl is simply the change in the kinetic energy, half mv squared. But this here we've just shown equals to minus q d phi, right? Just a change in the potential energy. And so ultimately what I can do is I can write, or I can have something that is a constant of motion. So the change in half mv squared plus q phi equals to 0. And so the term inside the brackets, and I can give it some symbol, h, is just a half mv squared plus q phi is a constant of motion. Okay. Because the d change of this is always equals to 0. And it turns out that this for conservative systems, well, this is also the total energy. Total energy. Total energy. And for conservative systems, this is the Hamiltonian. Okay, so we can see indeed the interpretation of phi is relatively straightforward. It's the potential energy of a particular field or a particular charge distribution per unit charge. Okay, and so it has to be included when we consider the total energy, right? So kinetic energy plus potential energy, and so even when we do classical dynamics, when we consider the Hamiltonian, this is a term that then enters into. I hope that people can also see the analogy with the gravitational force as well. Okay? Because here we've considered the electric field, but in our entire derivation and everything that we did up to here, there's no distinction between what kind of field we're talking about. Right? Conservative field is just a conservative field where, F over some loop equals to 0. And so we can actually show that the gravitational force, at least the Newtonian one, is conservative. So all of these calculations also hold for the for Newtonian system, Newtonian gravity system. Okay, now let's consider the following thing. So let me quickly just work for the electrostatic. Now let's move on and let's actually consider fully the electric field, because we've so far only used one equation, that is that the curl of E equals to 0. And from that, we at least know that the field is conservative. But we have the full field to consider. And actually, this will lead us to showing the so-called Poisson equation. And it will be clear in a moment why that is the case. Okay, so if we consider the consider the scalar potential and now in Gauss's law. Okay, and so Gauss's law simply states that the divergence of E equals to, and I'll write this down later, is minus rho over epsilon naught. And so in this case, we have that. Okay. I think I'm losing track of minus signs, but it's okay. This here is the divergence of a gradient with a negative sign, and therefore we have that this is the Laplacian. Okay, don't forget this is the Laplacian of phi equals 2. In this case, it should be rho epsilon naught minus that here. And indeed, if I combine the last two lines, I end up with the following equation. The Laplacian of phi equals to minus rho epsilon naught. I need to double check whether the minus sign is correct, but I can do that later. Okay, and this is indeed the so-called Poisson equation. Now, in what will come in the following weeks, this equation is the central thing. There's nothing more important to the study of, well, not nothing, but especially in electrostatics, it is the most important equation is the Poisson equation. And starting from next week, we're really going to consider how to manipulate, how to get solutions to this Poisson. For the time being, it suffices to say, and this is something that I've alluded to before as well, right? Remember when we looked at Helmholtz theorem, when ultimately the thing that I told you to assume is that the Poisson equation has a unique solution, and in this case, we can write phi in this case as a function of position as 1 over 4 pi epsilon naught integral of rho prime r minus r prime d prime. Okay. And for the time being, the solution here is something that I just hope you will simply accept. But it's something that, if time permits, I actually want to explicitly show why this is, why you can write the solution in this particular. Okay? But in order to do that, we need to delve a little bit deeper into the intricacies of this Poisson equation. And one thing that we'll also do starting from next week is to show that this is not just a solution, this is a unique solution. This is the only solution. Okay, so this is another good point to take a quick break, after which I want to wrap up a little bit about the vector, about the scalar potential before I move on and talk a little bit about the vector potential. Okay, so let's take a break and let's come back at 3:20, 3:27:28. Another 5 minutes to. Okay, I'll see everyone in a second. Okay, welcome back, everyone. Let me quickly open up the floor to see if there are any questions about what we've done so far. Let's get attention. If not, let's move on. And the next thing I want to do is consider the energy, right? Phi is a particular potential energy. In this case, let's consider the energy of a particular charge. Or actually, let's make this energy of the electric field. So in this case, let's consider what happens if I consider the potential energy associated with some charge, certain charge density. Okay? And so imagine the following: I've got some particular charge density here, some particular charge density. Now, in order to create this, we had to make this system. Okay? We somehow have to, if we start with nothing and we create the system, then what happens is that in order to assemble this, so to assemble rho, we had to do work against Coulomb force. So if you will, let's start with something that looks like this, and I bring a particular charge in. I bring a particular charge into this system. And so now we have to do work. So work against this existing here, let's call this rho prime. Okay. Now starting, if I put this in infinity, if I put this one in infinity, then it doesn't feel any force, it doesn't feel any field, and so it starts off with 0. And then as I bring it closer in, I'm doing work against this against the potential of rho prime. So somehow, therefore, I'm storing potential energy in a particular charge density. Okay. And so if I look at this expression over here, this expression over here, and I can see that the potential only depends on charge density that is already present. So the potential of, let's say, this rho prime, the potential of this, the potential that this small dq has to go through in order to reach, rho prime only depends on rho prime. So putting it closer does not change the potential that this rho prime creates. Okay. And the other thing, of course, recall that the electric field is conservative. And so we arrive at the conclusion that it doesn't matter, right? No matter how rho is assembled. since the phi only depends on the rho inside, and the field itself is conserved, so doesn't matter which path I take, then putting those two things together, it means that it doesn't matter how rho is assembled. In the end, the final energy associated with this charge density only depends on the charge density itself, and not on how I've taken the particular integral or how I did the assembly. And under these circumstances, it actually helps us, or it makes things much easier when we consider, when we can consider, or we can ignore how the charge is assembled. And so we do a little, like a small mathematical trick. Okay? So instead of doing, and then this is, I think, what Griffiths does is brings, certain charges in and out in a rather, from my point of view, a rather complicated way. Instead, what am I going to do? I'm going to assume that I am going to, from 0 all the way to my final. Okay, so we want to consider from 0 all the way to some charge distribution. This is the goal. But instead of, or even considering some arbitrary one, I'm going to do it in such a way that the growth of rho is proportional to rho itself. So what does this mean? It means that I keep the distribution the same, and I'm just going to put layers on top, but in exactly the same shape as rho already was. So in other words, I'm going to scale. I want to scale the charge proportional to the final charge distribution. So in order to do that, I introduce a parameter, eta. It goes from 0 to 1. In such a way that the particular charge density of let's say an intermediate step is given by so charge density of intermediate step is eta rho. Okay? And so in this case, I can build up from 0 to rho by simply letting eta go from 0 to 1. And so in this case, total potential energy E can then simply be given by UE integral from eta from 0 to 1, and then a triple integral, consider the entire charge. So this is the charge density is given by eta rho, and if I want to go from 0 to 1 is the eta. Now the energy associated with or the potential energy associated with a particular charge density is then the charge density times the potential phi, and then all I need to do is d eta dv. Okay. I'm building up from 0 to some rho by sliding this parameter theta. Now this by itself should be relatively straightforward to evaluate. So I can actually split this integral in two ways. I can do the eta, eta, the eta, and then of course the rest just over some volume dv. Now the first part here, this part here, is simply is simply the integral of eta from 0 to 1, and so this gives me, as the answer, it gives me a half. So I end up with something a half times integral of rho phi dv. Okay. We're almost there. And so now, do we have, I can now evaluate this using Gauss's law. Okay. So now we can further rewrite this. Right. Using Gauss's law. So I get UE, potential energy in the field, is a half triple integral rho phi dv. Okay, this is the result that we had from last slide. And now I can write in terms of phi, I can write, I can simply use the Gauss's law. Okay, sorry. So this here, rho, I can now write what I had before was indeed that the divergence is rho epsilon naught. Indeed, this is epsilon naught over 2 integral of phi times the divergence of E dV. And now I can do some, differential operator manipulation that, hopefully we're starting to get more and more familiar with, especially since the last few lectures. So at this stage, what I can do is I can use the product rule, or I can rewrite the product rule to introduce two terms. So this is just the integral here, and here I can simply write this as the divergence of phi E, right, of the product of a scalar field and a vector field, and I subtract minus the gradient of phi dotted with E. Now, the first part of this integral is something that hopefully we start to recognize, and actually it turns out that we can make this vanish. So let's consider the first part of this integral. So let's split the two integrals up. So this is a half epsilon naught. And so I do this triple integral of the divergence by E dv minus integral of the gradient of phi dotted with E, again dv. Now, so the first part, I can actually use the divergence theorem again, okay, or Gauss's theorem. And so here I can write the first term as the double integral over some closed surface of just phi E ds. And of course, this one remains this. And again, I can now look at this expression over here. If I look at the top one and this one, then in principle I can evaluate this all the way out to any volume that I wish. as long as as long as the fields vanish at infinity, and the individual contributions, if I make this volume very, very large, doesn't matter, right? Outside of a particular volume, then the fields equal to zero. So I only have to consider what is I only have to consider elements of where the fields are non-zero, but I can put the volume, I can integrate this volume to anywhere that I want. Now, alternatively, if I look at this element over here, then I'm allowed to place the surface anywhere that I want. This is a trick that we've seen last time as well, right? In principle, I can put this, surface anywhere, and suppose I put this surface at infinity, then as long as the fields vanish there, then I'm good, right? This thing goes to zero. So indeed, I can make the second term vanish, and I can also, of course, specify that this here is just minus e again. And so I end up with a particular expression of epsilon over 2 integral in some volume e dotted with e. And so the density, so the potential energy density, let's call this small u, e, is simply given by half epsilon e squared. Okay? Or if you want to write it a little bit more rigorous, I can do the modulus of e squared. This is actually this is a rather profound result, and it's good to at least stop here to think a little bit, and that is that this E itself, so the field itself, can be related to some energy, some potential energy. And again, we go back to the very first lecture, right? Remember the very first lecture when I mentioned that, that the introduction of a field really led to a revolution in terms of kind of thinking in terms of physics. Instead of action at a distance, where something only exists when there's some force being felt, being applied, or some change of direction. Very Newtonian experiment thinking. Here, this is another kind of conceptual indication that these fields are actually quite fundamental, or actually exist, right? Because I can associate a particular energy density to the field itself. You don't need a test charge to be there for the field to exist. The field itself exists. And this is actually quite an important result to consider. Okay. Anyway, so this more or less closes out the discussion that I wanted to have regarding the scalar potential. Okay. So I know it's a little bit quick. We only had about 20 minutes, but I want to take another quick break here to before I move on to the next part, where we consider the so-called vector potential. Okay, so let's take a quick break. 5 minutes, maybe a little bit too much. Let's do 4 minutes. Let's come back at 3:51. Okay, just a quick break, and then we'll we'll continue with the vector potential. You guys in a bit.
Excuse me, Professor.
Yes.
Can you explain once more time why the surface integral of E dot ds will vanish in the last page?
This one?
Yeah. With two green arrow.
Right. Okay, so the point is the following: is if you are allowed, right? If this integral holds, irrespective of where you place the volume or how far you integrate out to, and then that also means that I can, in principle, integrate all the way to infinity. Now, if I'm allowed to put, the volume integral, if I'm allowed to integrate all the way out to infinity, then the surface S here, right, this bounding surface, is the surface at infinity. And so the terms, phi and or E, we don't even need to specify, right? Even if one of them vanishes at infinity, then the surface integral vanishes. Right? So basically what I can do is I can push the consideration of the surface all the way out to infinity. And so if the field vanishes at infinity,
So we are doing the integral to infinity in this case.
yes, that's a very critical thing. In order to write the expression here, and this is a caveat that I'm pretty sure Griffiths actually makes very explicitly, and this is something that you have to really bear in mind. This expression only works when you integrate all the way out to infinity. Okay, and Isaac makes a good point. Okay, this is only considering a localized distribution. If I have, for example, one slab of electric charge that goes all the way out to infinity, it doesn't matter how you can make it or not. This is something that then will no longer hold. This energy density is only defined for localized charge distribution. Okay. Does that answer your question?
Yes.
But this is an important trick, right? I can't stress enough. This is actually something that that typically pops up occasionally, and that is, the use that, when you have a gradient of something, then, it doesn't matter if it's, let's say, a localized charge distribution, then I can get rid of all the boundary terms, all the surface terms. Sorry, yeah, boundary terms. Because I can, in principle, push it all the way up to infinity. But, what Isaac's saying is indeed correct, right? So this only considers localized charge distributions. Because remember what we did in previous, what we did when we started off, and that is if we have, we want to bring particular charges from infinity, where there's no force, there's no field, and we bring it all the way to a particularly localized charge distribution. But, this would not work if I consider, an infinitely large, in whatever dimension, direction, charge distribution. That wouldn't work, because then there's no way I can bring something out from infinity all the way to that particular point in order to make that charge distribution. So for anyone who uses this, this is a big caveat that that you should bear in mind, and that is that this is an expression only valid for localized charge.
Only valid for
Localized charge distributions. So I can't, like, if the situation is such that I'm considering, let's say, an infinitely large slab of charged surface, then I can't ask, okay, what is the energy in the field? I can't give it this formula here. Then I actually need to consider the actual potential energy, and then deriving from that the charge, the potential energy or energy density.
But why would that be? Why would there be a difference between the Gauss law in integral form and that?
So it's not about whether we consider Gauss law in integral form or not. It is whether this term can disappear or not. If I'm considering an infinite, like a non-localized charge distribution, then there is no, then this does not automatically disappear at infinity.
Okay, thank you.
Yeah, good question. Good question.
Professor, in the last sentence, you write down potential energy density. This is density or the total potential energy for a localized electron package.
Okay, so this is it's sometimes difficult to use small u and big U, but all that I've done is I've taken away this integral, right? So I've only looked at this portion inside here. So this really is a density in the sense that I need to integrate over a volume.
Oh, okay.
And in this case, the entire space.
Oh, and can you say once again that not from the mathematical way why the potential energy density is equal to half epsilon naught electron square, electric field square?
Sorry, say that again.
Any physical meaning that the energy density is proportional to the electric field magnitude square, not from the mass.
Any physical intuition? Yes, yeah. I think maybe what I would say is that the best kind of physical intuition comes from. So with anything, the physical intuition is typically kind of, it's more inside yourself. I'm not saying this is the truth, but this is kind of how I see it. So in order to consider the actual, let's say the charge, like when we talk about energy, we typically have a Q, the charge, and then the field, E. Okay? Or in terms of energy, we can consider this as some phi. Now, what we have here is two things, right? We have both the charge, which I know by itself is related to the field, right? Or generates the field. But I also, in order to make this kind of an energy, I also have to have a look at the potential, which is also the field itself, is also related to the field. So in order to make this kind of, in terms of energy, I need two pieces that are related to the field, right? I've got the charge density, which is related to the field, and I've got the potential, which is itself related to the field. So it makes sense that there are two pieces of E there. And then of course the half is there to avoid if you do the counting exercise that Griffiths does, is avoid double counting. But the half is basically kind of there to regularize things, and not terribly important. But you're right. The fact that there's two E's here, two pieces of E comes from the fact that you need the charge and the potential. Both of them are related to E. Okay, let's go to the chat. This is actually good. We have some discussion. The last expression. So I'm going one by one. Okay, I'll try to get through all the different. Does it mean that the last expression with two terms is true for any volume? But we take the volume to infinity to have more convenient view of the density. No. Okay. This only holds if I'm allowed to put. This only holds if I integrate all the way out to infinity. Of course, there are if the field disappears in places even not at infinity, then that's fine. But typically for localized charge distribution, the field only is zero at infinity. And so this expression has to be integrated all the way out to infinity. So Ling is asking whether I can explain how the 1/2 comes from. It's a little bit tricky, and maybe one thing that I could recommend you doing, maybe to get a different insight, is to look at Griffiths. I can look up the page where this is, and this half basically comes from, again, the following thing, right? See here that we have two things. We have the charge and we have the potential. And both, as I said before, contribute one factor of E. But the problem here is the following, is that, if I take both rho and phi to be kind of in its final form, then I will have done what we call double counting. I have both counted the contribution of rho and phi. But I can't do that, right? I can't consider the field or the potential of phi of rho itself, right? Because the premise is indeed that I'm bringing some charge from outside here in. And so I have to exclude, right? I have to exclude, like technically I have to exclude from phi the element of rho, like a small element of rho, then I have to exclude that from phi if I'm building this up. But here I'm using both the final form of rho and the final form of phi. So in essence, what I've done is I've double counted, right? So I can't use both rho and phi in its final form without actually adding this factor of 1/2 to avoid that I'm also adding up the field, the scalar field, that is the potential that is generated by itself, by rho. That's why I need a factor of 1/2. Okay, the next question, it looks like when you integrate E. Yeah, I don't know whether that's a question or comment. I don't know what you're trying to ask, so feel free to rephrase your question maybe. I'll move to the next question first before coming to yours. So that means if the charge distribution does not span to infinity, then consider E field a very far away, the term vanishes. E field vanishes, yes. And if the E field vanishes, then the surface if I put it out to infinity, also vanishes. Okay? Now, of course, if I have an infinitely, like a charge distribution that spans all the way out to infinity, I can't do that, right? I can't consider this term over here at infinity, then it would not be zero, it would not vanish. And that's why Isaac was correct in saying that this only holds for a localized charge distribution. Okay, any other questions before we move on? But anyway, I appreciate the questions. It means that people are actually listening. Whether or not I explain it in the right way for you to understand, it means that at least people are paying attention. So I appreciate that. Okay, I don't see any other questions at the moment. Again, we'll have some time at the end of the lecture to ask further questions. So why can we consider the E field very far away? So one way to maybe see this is the following here. Let's say in this expression over here, right? So in principle, I only integrate over my charge distribution to get UE. But even if I integrate, so if this is the charge distribution, right? If this is rho, then in principle, I can integrate, exactly here, exactly to the edge, like this. So this V, indeed, just at the edge. But it doesn't matter, right? Because even if I integrate here, for those pieces of volume that is outside of the charge distribution rho equals to 0. There is no charge density out there. So all that I'm doing is, even if I'm integrating V, to a particular volume that is outside of the charge distribution, then this here, rho phi, simply equals to 0. And so it doesn't matter where I integrate out until. I can integrate all the way out to infinity. And any place that is outside this, the space where rho exists equals to 0. So I'm just adding zeros. So in this case, this expression still holds. And I integrate all the way out to infinity. And that's actually the thing that we end up using, so that I can consider this in this surface here. I can consider this, at infinity, and I can show that that disappears. Area becomes big. Well, E is, let's say, like E is 0, right? So it doesn't matter how many zeros I add up. If E goes, okay. So let's look at this specific one. Okay, what is let's say a point charge. So this is actually a question for everyone, but Q, you can answer as well. If I put E, how does E fall off with distance? Do you know? Okay. What about the potential? How does that follow with distance? 1 over. Okay, good. Okay, how does S, the surface, grows with distance? R squared. Okay, so here, that's another way to see it. Here we've got a term that then goes as that's because your phi tends to 0. Okay. 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 This is now getting. Let's do this at the end of the lecture. Okay. I also don't want to keep everyone here and not being able to finish it. So Q, why don't you stay on a little after the lecture? We can consider talk about this. Okay. Okay. Appreciate the discussion. Let's have this at the end of the lecture. Okay? Because I do want one. Okay, I do want to add. I do want to continue. So let's hold this discussion for the end. The last thing I want to do today is to discuss the so-called vector potential as well. Vector potential as well. And the vector potential actually comes in as the other side, as the flip side of the magnetic field equations. And so we know that the magnetic field is solenoidal, meaning that the divergence of B equals to 0. We also know that the divergence of a curl is 0. In this case, we have that the divergence of a curl, old habits, let's do this one, of some A equals to 0. And so indeed, we can write the magnetic field as a curl. So B, I can write this as the curl of some A. Okay, and this is in contrast to what we started off with in this equation here, right? Here we started off with the electric field where the curl equals to 0, and therefore we get to write the electric field as a gradient of a scalar field, and that's a scalar potential. And here we have the flip side, with the opposite, where we can now write that the divergence of B equals 0, and therefore B is related to the curl of a vector field. And so here, what we can write indeed is A here is now called the vector potential. Now we can again ask the question: okay, what if I now I can write B as a curl of A. Then what happens if I now consider the other magnetic field equation? So the other magnetic field equation simply states that the curl of B equals to mu naught J, but the curl of B is also the curl of A. Sorry, the curl of B is now the curl of the curl of A. And using our vector, you know, our differential operator identities, we know that this is just the gradient of the divergence of A minus the Laplacian of A. And so we arrive at this particular form where we can write that the Laplacian of A equals to mu naught J. Let's see if I do this correctly. This one, nope, the other that. Right. The divergence of the gradient, sorry, the gradient of the divergence A minus mu naught J. Now, this is something that when we looked at Helmholtz theorem, we saw as well. And when we did Helmholtz theorem, the point here where we ended is that as long as the divergence of A is specified, and of course, assuming that J is something that is known, then this is completely, this is a Poisson equation that you can solve. Right? It has a unique solution. And so that was the basis on which last time around when we looked at Helmholtz theorem, we said that, the crucial thing is that, the divergence of A is specified. But here, I'm going to go a step further and say if, okay, and I'll underline this, if the divergence of A equals to 0, then I get something that looks like a very neat Poisson equation again. And this is actually important because this allows me then to write the following, that A is simply mu naught over 4 pi integral over V of A divided by R minus R prime dV prime. Okay. And this is just, again, because this is a solution to the Poisson equation. Now, it should be noted that this here is actually not just one Poisson equation, but there are 3 Poisson equations, one for each coordinate. Okay, that's a big caveat. So the Laplacian of this vector field A is simply Laplacian of, in Cartesian coordinates, is the Laplacian of A, of the x component of A, of the y component of A, and of the z component of A. Okay. Now, there's a little subtlety here, and I want to a certain extent, I want to discuss this with you already at this stage, and that is basically this thing over here. In order to achieve the result that we achieved to get Poisson equation, we had to specify that the divergence of A equals to 0. And in a way, this is both subtle and important, because if we go back, we know that we know that B. Oops, we know that B equals to the curl of A. So indeed, in order to specify B, if we want to, fully determine B, then we must also specify the divergence of A. Okay. Okay. Actually, no. Let me do this properly. So if I want to determine B, I need to fully determine A. but I only know what the curl of A is. So I also need to know what the curl, what the divergence of A is in order for me to be able to fully specify A. And therefore B. Okay. So indeed, this the determination of the divergence of A, it is important, especially in this field. Okay. Now, another way to see this, or another way to consider this, is that, you know, even though if I know A, I can calculate B, but, you know, I can always, because the curl of a gradient, and let's call this some function f equals to 0, I can always add gradient to A without without changing B. In other words, I can write that the curl of A plus the gradient of some function f is simply the curl of A, and that is B. And so basically what happens is that I have an infinite freedom. We have an infinite freedom to choose A, and the specific choice, I can do so by specifying the divergence of A. Specify, and so I can use this infinite freedom to choose A by specifying the divergence of A. And that's the key. And so the choice, right? So the specific, sorry, I don't know, that should be equals to 0. Then I already made a choice. Oops. Okay, so I have to specify the divergence of A. But I have an infinite freedom to do so, right? Because I can always add the gradient of some function, some scalar function. And this choice, or the particular choice of the divergence of A, is so-called the gauge. And it turns out that we have the freedom to choose A in order to make our equations easier. It does not change the magnetic field. So in this case, what we did is we made a specific choice. And we said that the divergence of A equals to 0. And then the equations come out in such a way that the Laplacian of A equals to minus mu naught J. Right? And so you get Poisson equation. But this, this only comes out when I've made the specific choice for the divergence of A. And we'll see very, almost to the end of the lecture series that this is not a unique choice, right? This is what I've just shown, right? I can always add the gradient of that. But that, when I consider dynamics, then especially waves, electromagnetic waves, then often it's the choice of gauge is easier to choose a different gauge, just so that I get an easier wave equation out than it is to get something more complicated. Okay, so this pretty much ends the discussion on the potentials. Okay, so this is basically an alternative formulation of the electric field and a magnetic field, right? And simply stating that I can rewrite the electric field and a magnetic field using potentials, right? A scalar potential or a vector potential. For the electric field, it makes sense to consider the scalar potential, because a scalar field only has one value for each position, instead of three that you have for the electric field. But for the magnetic field, it doesn't really make a big difference because we're considering a vector field. But actually, as we'll look at examples of how to do these calculations, this is what kind of the next section of this lecture course is about: is how do we do calculations under this formulation. We will see that occasionally it is easier to first consider the vector potential, and then take the curl to get the magnetic field. Okay? But ultimately, as you can see, it comes from Helmholtz theorem that we are allowed to express the E and the B field in terms of scalar and vector potentials. Okay, that pretty much ends today's lecture. I'd be happy to open up the floor to either continue the discussion that we had just now, or any other new questions. So let me ask at least Q, is your question answered? Seems like there was some consensus reached. But I really want to remind people though, and this is something that, again, I'll say it nicely for now, but really use your full name when you log in. Okay, this is just for safety for everyone. It's almost the same as needing to show your student ID. So this goes with for Maxwell, for N, for Q, Tommy, and all the other people. Like I would really appreciate, and I think it's also for the safety for everyone else, if you can write your full name. I don't want to be policing this, but I think hopefully you can. Okay, so Q says the question is answered. Take phi at infinity equals 0. Oh, no, it's that the integral vanishes if I take the surface if I take the surface to be at infinity. And that's what Isaac is saying. So.
Professor, I have some problem about Blackboard. Can you turn on the function that we can resubmit our assignment or honesty form?
Yeah. Okay, yeah, I hadn't appreciated that. I only did it once. Yeah, so in case of mistakes, you should be able to do it again. Let me, I'll make a note. Isaac, can you remind me to, actually, I think Isaac, you should be able to change that. Can you make it such that there's an infinite amount of submissions for the honesty form? Yeah, it should be, if you go to the assessment, you should be able to say whether it's allowed to have multiple submissions. And then just do the last one that counts. Okay, yeah, thank you. I will make sure that that is fixed.
Thank you.
No problem. Any other questions? Okay, let me turn off the recording, and then we could take other